Hello everyone. Today, Betty and Jackie are going to talk about how we determine if a series is converged or not. And we will start with the first example.
Hi everyone, I'm Jacky, and now I will going to use an example to testing if the series is convergent or not. And here we will come to our first example. It is the summation of n from 0 to infinity with the numerator of n factorial and um, a kind of patterned denominator with 3n plus 2. So the first one is 2 times 5 times n, blah, 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 until 3n plus 2. And then we're going to analyze how this series will work if it is able to testing. So we are going to test if the n is approaching infinity, will this whole thing approaching 0? So for each term, obviously the first term is 0 factorial over 2, and the second is the 1 factorial over 2 times 5, and the third one is 2 factorial over 2 times 5 times 8, and blah blah blah, it goes on. As we see, it is very obvious to show that the denominator is increasing faster and faster than the numerator. So for each term, it is generally approaching 0. It has become smaller and smaller and approaching 0. So we can, since the individual terms of the series approaching 0 as n approaches infinity. So then the summation of the series from n from 1 to infinity might converge. And then I will pass to Betty to explain the more detailed explanation.
These series terms are very easy to be cancelled out, and so we are going to use a ratio test to test if this series is convergent or not. So the ratio test basically says that when the limit of n approaches infinity, the absolute value of an plus 1 over an is less than 1. Then the original series converges. So in this case, we apply the an plus 1 over an into this original series, and we get that the limit of n approaches infinity of an plus 1 equals to n plus 1 factorial over 2 times 5 times a times blah 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 3n plus 1 plus 2. So it becomes n plus 1 factorial over 2 times 5 times a times blah blah 3n plus 5. And then we times the reciprocal of an, which is 2 times 5 times a times blah 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 a 3n plus 2 over n factorial. And then we can see that both an plus 1 and an starts with the term 2, because the 3n plus 5 only 3n plus 5 and 3n plus 2 only applies to the last term of the series. And then we cancel out some of the terms, like the n factorial can cancel out with n plus 1 factorial and leave only with n plus 1. And the 2 times 5 times a can be canceled out and leave only the last term of an. So we are left with limits of n approaches infinity, the absolute value of 3n plus 5 n plus 1. And as n approaches infinitive, this at the nth power is the same or 1, and this does not matter. And so this equals to 1/3, which is less than 1. So that we can conclude that the original series convergence. And because the ratio test not only tells tells us that the original series converges, but also tells us that this is a absolute convergent. So we conclude that the original series is an absolute convergence. And we'll move to another example and using a different type of test. So we will begin our second example of the convergence test. So this is our second problem, which is the summation of n equals 1 to infinitive of arctangent n over n times square root of n. And we can rewrite it as the summation of n equals 1 to the infinitive n to the 3/2 power and arctangent of n. And then we look at the arctangent of n first. So arctangent, we can use the arctangent and tangent of x to see the pattern first. So the arctangent of x is the inverse function of tangent of x. So that means that the graph are reflected by the line y equals x. And it also tells us that the domain of tangent of x equals to the range of arctangent of x, which is from negative pi over 2 to pi over 2. And please note that we use x to see the pattern instead of n, because x refers to all real number in these functions, and n only refers to natural numbers in the original series. But both arctangent of x and arctangent of n approaches pi over 2 when the variable approaches infinitive. So this part is approaching to a fixed number. And this part, it is easy to be identified that it is very likely for us to use the p-series for the further convergence test. So we're using the comparison test using the p-series to test if this original series is convergent or not.
And now we are going to use the comparison test and the p-series to identify if this series is convergent or not. Since we can see from the graph, the function is always approaching to pi over 2, so we can be seen from the graph below that the arctangent of x is bounded over by y equal to pi over 2. Therefore, the original series, we can expand out the original series to arctangent 1 over 1 to the 3 over 2 power plus, and we plug in 2, 3, 4, blah, blah into the original function. And we know that the whole function is bounded by the y equal to pi over 2. So if we substitute the numerator to pi over 2, the whole series, the sum of the whole series will be smaller than the comparison series, which is substituted with pi over 2 as the numerator. And each term of the of the arctangent n must be less than pi over 2, as arctangent x is bounded by pi over 2. And all we know that we can factor the pi over 2 out, and we have the numerator of as 1 for each term. And then, for the rest of those terms, we can easily know that it is the summation of n equals to 1 to infinity of 1 over n to the 3 over 2 power. For this one, we can use the p-series to identify if the comparison series is convergent or not. So, the original series is smaller than the comparison series. And this convergence series is and allows for the p-series test to conclude that since the p-value, the 3 over 2, is larger than 1, then the original series is smaller than comparison series, which is equals to a fixed number L. If the original series is smaller than a fixed number L, hence the original series must be convergent. And those are the two main methods we explain today: the comparison test and the ratio test. And now we're going to give you some practice for later developments. Here are the 4 practice problems for you to try to solve the problems. Please pause the video and we will show the answer in the next frame. And here are the solutions for the 4 questions. Please check your answer.
Thank you for watching this video, and we hope that this is helpful.